When we talk about things that are rolling, sometimes things are sliding and rolling at the same time. The classic example being a bowling ball. As the ball goes down the lane, it starts off not rolling very quickly, but doing mostly sliding. Now, friction between the lane and the ball will gradually increase the rate of rotation, and at some point, when this non-slip condition is met, when V equals R omega, then the ball is no longer sliding at all and is only rolling. We're going to figure out how can we find when that is true. So here we're going to try to find how long this bowling ball is going to be sliding. So to start off with, our bowling ball is rotating around its axis, the center of the bowling ball. That's the axis of rotation. And the only force acting on it is the force of friction between the ball and the floor. Our ball is moving this direction. So the force of friction is what's going to start it rotating and what's going to slow the ball down as far as linear velocity is concerned. Now our goal here, we're looking to find when does V equal R omega. So we need to look at both the velocity and the angular velocity. Let's start off with the linear velocity. So we'll start off with, we need to find a function for velocity with respect to time. So let's use v of t equals v initial plus at. Now we're looking at linear stuff here. So we know the initial velocity is 5 meters per second, and we want time to be our variable, but we need to find something for the acceleration. And we can do that by saying our force of friction equals ma. Okay, so if we do some rearranging and plugging in, we'll say that mu mg equals ma. Therefore, our a equals mu g. But we're going to say that this a is negative because our force is acting opposite to the direction that we're going. It's going to be slowing us down. So if we plug this a back into our original equation, we're going to get v of t equals v naught, which we know, minus mu g t. Okay. So far, so good. Now let's look at the angular. So we're going to have to get a similar function for the angular velocity. So we know omega of t is going to equal omega naught plus alpha t. So we need to find a function for, we need to find an expression for alpha. We know omega naught is 0, so that's helpful. We can just go ahead and make that 0. But we need to get something for alpha. Now we know from torque that I alpha equals FL. Now in this case, I, as we're told, for a solid sphere is 2/5 mr squared. So we can say 2/5 mr squared alpha equals, our force is the force of friction, so mu mg, and L, our lever arm, our force is acting on the outside of the ball, so our lever arm is going to be the radius of the ball. Now this radius will cancel out with one of these, and then we're going to solve for alpha. So we end up with alpha equals 5/2 mu g over the radius. Now we can plug this back in here and rewrite our expression. So we'll have omega of t equals 5/2 mu g t over r. So we'll keep that in mind. Let's put it all together now. We know v equals r omega is our goal. We know a function for v and a function for omega, so let's plug those in and see what we get. So for v, we know v naught minus mu gt equals r times our function for omega, which was 5/2 mu gt over r. Okay, so we see that our r's cancel out, so we really didn't even need the radius or the mass of our bowling ball. And then we can rewrite this a little bit. So we'll have v naught, which we know, minus mu gt equals 5/2 mu gt. If we rearrange, solve for t, plug in the numbers that were given in the problem, you're going to end up with t equals 1.822 seconds. Once you have the amount of time, then you could find how far it goes down the lane, or you could find what its velocity is when it finishes, just using kinematic equations.